Today, and the first speaker in the afternoon is Professor Barbu from University of Cluj.
Yes. Cluj in Pennsylvania.
Professor Barbu from Romania, not from Transylvania.
Not from Transylvania.
And he from University of Iași, correct? And as usual, he will speak about his title. He will tell us later.
Thank you. Well, in fact, my talks, I'm going to give 3 talks to discuss about, well, as I mentioned, deterministic nonlinear Cauchy problem in Banach spaces versus stochastic. In fact, we are considering these 2 equations. The first is this deterministic equation, AX. Let's put in this form multivalued. This is not important. T0 T. Cauchy problem, x0 equals x. And its stochastic pair, dx plus ax dt equal, let's say, dwt, t0 t, x0 equal x. In fact, both equations might be also time dependent. I remember about A. Here, A is a nonlinear operator from dA in a Banach space, let's say, okay, I denote it by x variable, let's say y to y. And the usual condition, in fact, to have existence or a good to this problem, in fact, deterministic one to be well posed, is this operator A to be M-accretive. A accretive or quasi-M-accretive. This means
in the first equation, where does the equal sign go?
No, it's not equal signs. It is exactly okay. It belongs to. We can put the same thing here. It is not a very orthodox notation, but this means, in fact, this equation might be multivalued. This is exactly meaning. Okay, you can take 0, but A equal, and it's okay. Here, A is M-accretive. Accretive means, in fact, roughly speaking, that this operator, A plus lambda A minus 1, is Lipschitz with Lipschitz constant 1 for H lambda positive. In fact, this is the main assumption, in fact, under which you have good existence result and uniqueness result for equation 1 in deterministic case, and that also it is used in stochastic case. My discussion here is a comparative study of these 2 equations. I want to mention that for equation 1, for this nonlinear Cauchy problem, we have quite a complete existence theory now. And this theory, in fact, is from early 70s, in fact, and you can say that it's complete as far as regard existence, as regularity, and so on, other things. As regards equation, stochastic equation 2, of course, the theory is not complete. We should say that only for a quite few classes, or for quite a few operators of this type, we have a good existence theory. We can perhaps mention not more than 10. Now, we have a good existence. For instance, there is a case when A is a linear operator plus a local Lipschitz operator, which is not very good for application, of course. We have also good existence theory when A represent parabolic semilinear equation, reaction diffusion type. Now, also have a good existence in the case on Navier-Stokes 2D. Porus-Midi equation quite recently, and perhaps we should stop here. So we do not have in this moment existence theory for equation 2 equivalent or comparable with equation 1. This is exactly the theme of my talk, to explain why. First, to see what we have is for this deterministic case. That means a basic theory in deterministic case. I'm sorry for the people who are familiar, but I should repeat today in order, in fact, to compare with stochastic case what we know about equation 1. The conclusion is that, in fact, we cannot have or cannot extend completely basic existence theorem from equals 1 to 2, and I'm going to explain why. However, we can use a lot from the existence theory from deterministic case to general equation of type 2. This will be, in fact, the conclusion of my talks. So, I'm going to treat the following 3 topics. First, a survey for equation 1 when A is time independent.
And of course, you don't assume linearity.
No linearity at all. No linearity at all. Sometimes A can arise as semi-linear operator. Linear operator plus some perturbation, but not linearity, of course. So the first I survey the existence theory in the case A time independent. From stochastic point of view, this is not very important, as you'll see. But however, it is good to remember it. Secondly, we treat the case on A is dependent of time. This is a hard case. It is important for stochastic equation, and we'll see exactly what we have and why we cannot completely apply the existence theory for time dependent to stochastic case. And finally, 3, we'll treat some stochastic case. In fact, there will be a survey and some new results with many proofs in stochastic case, which are not covered exactly by the case 2. This is exactly the plan of my talk. So let me first recall what we know in this moment. They are not very recent results, they are already standard results, but I want to mention for the people who are not familiar with this method. So what we know about Cauchy problem here. Here we have a big result and general result which has origin in the so-called Crandall-Liggett theorem, which is a fantastic theorem. In the moment it was established, it was surprising because it was possible to get in a nonlinear case, in a so general nonlinear case, a result equivalent to Peano theorem, because it's Peano theorem. This is exponential formula of Liggett, Crandall-Liggett. It is infinite dimensional version of Peano theorem. So let me recall first this result. Well, first, if you have equation 1, by strong solution to this equation, we mean, of course, strong solution to equation 1. We mean, of course, a function x, which is in the Sobolev space 1, 1, 0, t, y, which is almost everywhere differentiable, and satisfies this equation 1 almost everywhere. This is strong solution. Well, we'll see under which hypothesis we have a strong solution. Now, we'll define so-called mild solution. What do you mean by mild solution? Or integral solution, because it is an equivalent and different name under which this mild solution or weak or generalized solution arise in literature. A mild solution, roughly speaking, is a finite difference approximation, or is a limit of a finite difference approximation of the Cauchy problem. Let me be more explicit. If you have equation 1, we call, and for each epsilon, we define as epsilon discretization of the problem. Epsilon discretization of a problem, this means that we take t0 equals 0, less than t1, less than tn equal t, and fi such that sum of integral ti minus ti from ti minus 1 ti from ft minus fi, the norm from I equal 1 to n is less than epsilon, ti minus 1 less epsilon, and finally we take zeta I plus 1, solution to this different scheme, t plus t minus t plus 1 minus ti, plus a zeta I plus 1 equals 0. This is a finite difference scheme associated with problem 1. For this, we consider zeta epsilon, which is a constant, piecewise constant function, which on the interval ti minus 1 or ti plus 1, it is exactly zeta I. So it is this piecewise constant function associated with this scheme. And now we have the definition.
Can I interrupt for a second?
Yeah, please, anytime.
I would like to specify, to ask you for 2 examples you mentioned of one operator for which this applies for one.
I'll do everything, yeah. At the end, I give several examples.
But not at the end, right now, just even say.
Yeah, okay. Okay. Let's take a trivial example. The trivial.
Well, maybe not trivial. I mean, when I say 2.
Okay.
When I say 2,
Okay.
I meant
Okay, okay. For instance, an example of this M-accretive operator is this operator A equal, let's say 1. Not trivial, but okay, simple. Plus beta y, where beta is a continuous function, could be also multivalued, with a domain of A equals H01 intersect H2 intersect which y for which beta y is in L2, okay? And the space, in this case space y, is L2 omega. This operator is M-accretive, and equation 1 becomes in this case a parabolic equation dy dt minus delta y plus beta y equal f, with boundary condition on the omega equals 0, y0 equal y0. Okay, so this
Beta
is a standard
continuous.
parabolic semilinear equation.
Beta.
Beta is a multivalued graph which is maximal monotone. Might be, for instance, continuous, but it's not necessary, it could have jumps. But it is important to be maximal monotone. Maximal monotone means in this case as a range of 1 plus lambda beta is a whole lambda. This is. Okay. This is a typical standard example, but it's only one from a large variety of problems. Because what I'm going to say cover all parabolic problems, reflection problems, variation inequality, wave equation, also Navier-Stokes equation, a certain measure, we'll explain, Burroughs media equation, conservation law equation, and so on. So almost all processes, dissipative processes, are covered by this theory under a certain degree. That's exactly. But I'm going at the end to mention quickly. Yeah, please.
And I ask for the second example,
Yes.
which is of an operator which is not covered by your talk.
Which is not?
Covered by your talk.
Well, which are not monotone, in fact. It's a process where
just
we are not dissipative.
So for example,
not dissipative. Yes, I'll give you I'll give you some. Navier-Stokes is partially I'll tell you about Navier-Stokes. Navier-Stokes is not monotone. Inertial term is not monotone. But if you take a truncation, it becomes monotone. So Navier-Stokes can say that it's half covered, and we'll see exactly. But one example is not covered is the following. It is YTT triangle Gordon equation equal F. This is not covered, even if you write as a product space. But if you consider this equation, YTT minus delta y plus nonlinearity in velocity, this is covered. But even this problem, by using a truncation procedure, can be put into this form. Navier-Stokes formally is not covered, but we'll see in fact that it can be treated. By using this method, I'll call nonlinear semigroup method. In fact, it is monotonicity method. But coming back, what we mean in fact by a mild solution? A mild solution, we say that a function x, which is continuous in 0t x, is called mild solution to equation 1 if for each epsilon there is a discretization, there is an approximating solution zeta epsilon defined like here, such that zeta epsilon minus xt norm is less than epsilon for all t in 0t. So my solution is a limit of finite difference discretization scheme. This is definition of mild solution. There are several other equivalent, for instance, so-called integral solution in the sense of Bainilan, or generalized solution, and so on. But this one is the best, and also is constructive. So this is mild solution. Of course, each strong solution is also mild, but not, they are not equivalent, of course. Now, which is it? Yeah.
Is it possible to have a non-uniqueness
No.
for mild solution?
No. No. The result is exactly, I'm going to say so. It is, in a general Banach space, is A is M accretive, or quasi-M accretive. What means quasi-M accretive? This means as operator A plus omega I, some omega is M accretive. Cauchy problem 1 has a unique mild solution. This is a main result. It's quite a technical result. In the case when autonomous case f equals 0, this is a Crandall-Liggett theorem. Well, the original proof was very, very technically, but finally in the years, at the end of 80, there are several devices due to Kobayashi, Evans, and so simplifies the proof. So we have now quite a simple proof, but not so proof. It covers, however, let's say 12 pages. No, it's some combinatorical, in fact, it's some combinatorical proof. It's not trivial at all in general space. So the first result is this.
Excuse me, Z epsilon is what? Correct, this Z epsilon. Z epsilon is this Peano approximation in the definition.
Yes, this function here, it is called an approximating solution. This.
The right-hand side in the iteration should
So
be
this
zero.
is a this is in fact it is the epsilon discretization. The epsilon discretization associates this solution zeta epsilon, which is a piecewise function defined so zeta epsilon equals zeta I for t in the interval ti plus 1, so on. This is approximating solution, epsilon approximating solution. And the mild solution, we say that x it is a mild solution if for each epsilon there is an approximating solution with this property here. This is.
The zero should be f of ti.
Excuse me?
Zero
This
should
zero
be
is
f of
fixed.
t.
This zero is fixed, initial data.
The zero on the right-hand side.
No, here it is fi. I'm sorry. It's fi, it is exactly this. Yeah, sure. Now, which is the result? Fundamental result here is the following. If A is M accretive, or more generally quasi-M accretive in the sense that 10 for each initial data in VA bar, closure of the domain of A, and for each F in L1, 0, T, H, X, Y, this is a space, or X here, there is a unique mild solution for problem 1. And this solution is Lipschitzian with respect to initial data and right-hand side. This is fantastic theorem, in fact. Also, uniqueness is not trivial at all. And also existence, because to prove existence, we should prove that this finite difference scheme is convergent. And it is a big job, in fact. Big job. In general, this mild solution is not strong solution, is not almost everywhere differentiable. Not almost everywhere differentiable, but I'll come back about this. Let's take a corollary. A corollary of this one is a famous Liggett, Crandall, or Crandall-Liggett, okay, exponential formula, which is saying that if f is 0, then Cauchy problem 1 has a unique solution, mild solution, of course, xt, which is given by limit n goes to infinite I plus t and a minus 1 x for uniformly on compact. This is exponential formula. This is quite, okay, in finite dimension, this is exactly Peano's theorem. Find a different scheme, Peano, find a different scheme, which gives convergence. But fantastic it is true in a general Banach space, this exponential formula, in fact, because in fact, this exponential formula is equivalent with a finite difference scheme. Now we are computing step by step. Now it's not trivial. This is not a trivial theorem. Perhaps is the hardest part of the nonlinear semigroup theory. And it works for A M-accretive or quasi-M-accretive. That means that you can perturb M-accretive operator by Lipschitzian mapping, for instance, and still remain true. This is exactly quasi-M-accretive. Well, and there are many things here, because in particular, if f equals 0, we have a nonlinear semigroup of contraction generated by A on the closure of D A bar, on the closure of DA. There are many things related to generation, but I'm not going to present these things here. Let's answer to the following problem. When mild solution is strong solution? Here we have the following result. Sure. If X is reflexive, then mild solution is strong solution. This is the next result. Quite a general, but of course it excludes some important space, and L1 is perhaps most famous. Excludes L1, unfortunately. Now, this is a next result. Okay, I'm not going to give proof here because I only to review the results. Now, if, so let's say 2, theorem 1, theorem 3. If X star is uniformly convex, then this strong solution, of course, if X star is uniformly convex, it is reflexive, now, so mild solution is weak solution. So if then the solution, that's strong, of course, X can be obtained by the limit of the following Yoshida approximation scheme. By Yoshida approximation scheme. So that means X can be obtained by passing to limit in this equation A lambda X lambda equal F X lambda 0 equal X. But I forgot to say something in theorem 1. We have, it is true that the mild solution is strong solution, but we should assume if X is in DA, not in general, and F in W11 for strong solution, we need also this assumption, like in linear case. Now, if X is in DA and F is in Sobolev space, infinite dimension W111, and space is reflexive, then the mild solution is strong solution. Okay. Now, if X star is uniformly convex, then this solution, mild or strong, is limit uniform of X lambda when lambda goes to 0 in C on each interval uniformly. Y. So the solution can be obtained as limit of Yoshida approximation equation. Okay, Yoshida approximation of in Cauchy problem is very famous, and people like very much, in fact, this. In fact, if you want to treat nonlinear problems, you have two possibilities: to your Gagliorkin scheme or Yoshida approximation. Yoshida approximation has some advantages, and this is the reason it was used also for stochastic equation, because it does not change the space. Okay, Gagliorkin approximation, we should work on finite dimensional scheme. Okay, so this scheme where A lambda is a Yoshida approximation, that means 1 lambda I minus I plus lambda A minus 1, which is Lipschitzian and monotone and accretive and so on. So the solution to this problem is convergent to the solution to to our mild or strong solution. Yeah.
Actually, I think you have also said way of approximating your solution, the one which you have listed on the blackboard on the right, by your epsilon discretization, yes?
What do you mean? No,
Because you
excuse me.
mentioned that you can approximate solution by either by Galerkin or by Yoshida approximation.
Yes.
But there is also your...
Yes, we have another one. Yes, it's this one.
And you
It's
have
this
written
one.
it
Yeah,
down.
numerically, in fact, you are doing so. Yeah. Yeah, this is another one. Yeah, in fact, we have three. We have three possibilities, yes. Galerkin, but Galerkin does not work. Galerkin works very well in Hilbert spaces, but in Banach spaces, I don't know. You should find bases, big troubles. I mean, now, but Yoshida works quite well. This also in Banach spaces, if you know that you have a strong solution, this is convergent under certain situation. Okay. But if the space is uniformly convex, dual space uniformly convex, we have uniform convergence of this scheme. And this may be used to give a easy proof of existence, for instance, in Hilbert spaces. In Hilbert spaces, it's no longer necessary to invoke Crandall-Guess theorem, or because you can simply work with Yoshida approximation here, this equation, and can be proved convergence quite easily. It is exactly what happens in general. Now, well, the other properties as well, if the space is smooth, for example, is uniformly convex, in this case, it turns out the trajectory belongs to minimal section and so on, but I do not want to go into details here. I want to mention only one more thing. Why it is good, this approach, nonlinear semigroup approach? Because it's not only existence, but there are many other types of results. For instance, for our problem, let's take f equals 0. For our problem, we still have in this case, we have Trotter-Kato approximation theorem. That means if you have a family of operator A alpha which is convergent to A alpha goes to 0 in resolvent, the associated solution is convergent too. It's very important, in fact, is a structural stability of the system. It's also, this is not trivial. It is well known in linear case. It was proved first in Hilbert space by Prezis and Pazzi, and remain in general case here. 2, we have this so-called Chernoff formula, well known for self-adjoint linear operator, which also work in this case. For instance, I don't present Chernoff formula in detail, but it follows that limit, for instance, if you have two operators, A and B, M accretive, such that their sum is M accretive, it turns out that ATM over N, ABTM over N, X, N, when N goes to infinite, equal A plus B, T minus, put here minus. We have denoted by E minus AT, the solution to autonomous problem. That means the solution to equation, semi-group in fact, generated by A in this case. Now, this also it is true. And this represents the basis. This gives a possibility to approximate if you have, because very often our equation arises a sum between two M accretive operators. This formula, which in linear case is known as Trotter, in fact, formula, or Trotter-Lead formula, and so on. This permits, in fact, to decompose the calculus, because this formula say us that we can approximate the problem working separately with equation in B, fractional step method, in fact. It is the basis of this theorem. And there are many, many other results. So the semi-group, or this body of result, now permits to give not only existence, but many, many approximation results, regularity results, and in fact, is a unified theory. Unified theory, comparable with that in linear case. Let me say for the general case one more thing about regularity. So let's come back to our equation. 1 dx dt plus ax, let's take in this form, x0 equal x. So now it's clear. In general, we have mild solution if the space is not reflexive. If the space is reflexive and f is in W11, this is Sobolev space y, and y0 is in dA, we have strong solution yx, which belongs to W1 infinite. But the problem is the following. What happens if f is not in W11 and if x is in dA bar but not in dA? Do we have in this case strong solution? What exactly I mean? In linear case, we have analytic semigroup. Analytic semigroup have smoothing effect of initial data, and on the right hand side start with initial data in the closure of the domain, and the solution is pushed back in the domain and becomes regular. Now, this effect of entropy increasing effect. Now, it is something similar here. In general, not. We do not have the same theory, complete theory as in linear case. But what we have is the following, however. If if y is a Hilbert space, H, and if A is a subgradient operator, that means subdifferential of a convex lower semi-continuous function, then this Cauchy problem has smoothing effect on initial data, which is exactly the result in this case. The result in this case, let's say theorem 4, is the following. If x it is in dA bar, if f it is in L2, is not the most general, H, then the mild solution is strong solution, and we have that radical t dx dt is in L2, and radical t ax, or a section of ax, belongs to L2, 0t h. This means that you have good regularity in this subpotential case. What exactly means subpotential case? What I mentioned, A, it is d phi, subdifferential. Subdifferential is defined by d phi y minus zeta is greater than phi y minus phi zeta for all zeta, where phi is a convex function, lower semi-continuous. For instance, if f is differentiable and, okay, on per case, and it is convex, its gradient is operator of this type. But the result is very general now. It's true for every subdifferential of a lower semi-continuous convex function. Now, so in this case, you have this smoothing effect on initial data. Now, okay, I want to stop here with a general result because there are many others I don't. I want now to give examples to see which are the problem to which the general theory applies. I mentioned before that practically all problems of dissipative type of mathematical physics can be treated by this theory. So it has a unified character. So let me take a few problems covered by this general existence theory. Let's begin with the first one. Let's forget finite dimensional case. Finite dimensional case, you can take Cauchy problem associated with multi-valued maximal monotone multi-valued functions. So we have, in fact, existence here. But let's take non-trivial example. So the first I already mentioned. It's this equation, yt minus delta y plus beta y f y0x equal y0x with Dirichlet condition, omega. Dirichlet is not important here, could be very well Neumann or combined, so on. Where beta is a maximal monotone graph from A to A. In particular, beta might be continuous, but it's not the case in general. Beta is maximal monotone. In general, it's not everywhere defined. Could be the condition it is beta to be monotone, that if beta minus beta v, u minus v, it is positive, and the range of this function 1 plus beta to be the whole line. So we can have jump functions now, but remain maximal monotone. This is important. Now, okay, this we have a complete existence theory for this one. We can put also beta x here. This is not important, but because it turns out that this operator ay equal minus delta y plus beta y, domain of y equal y in H01 intersect H2. We assume that the boundary of omega is sufficiently small such that delta domain of delta be characterized by this, with beta y in L2, for instance, and the space, in this case the space y is H, it is L2 omega. This operator is an accretive. Moreover, it is a subdifferential. So for this problem, we can apply theorem 1, 2, 3, and 4, also 4. So we have everything about this problem. Beta might be multivalued. B multivalued is especially important in the case of so-called free boundary problem, parabolic free boundary problem. Parabolic free boundary problem, beta is multivalued, is not defined everywhere. Its domain is a proper line or a proper segment of the space of the line, and for instance one phase Stefan problem can be represented in this form. In this case beta is taken for one phase Stefan problem. Beta A can be taken this graph. Is 0 for A positive and is empty for A negative. This is one phase Stefan problem. But there are many other results. The book of Lyons and Duvois is full of examples of this type. So inequalities in mechanics and physics. So this is the first example. It is quite easy, immediate. You can put here on two lines if y0 belongs to, where it is a solution, and so on. No. Second example. Second example, let's remain also in parabolic case. Remains in parabolic case is reflection problem.
But
yeah,
before you go to the second, here you use a Hilbert space as
yeah.
y. What about some natural Banach spaces? Would also
Oh yeah, the same cube. The same problem can be treated. Thank you. It's a good question, in fact. I forgot to mention. It's not necessary. You can work directly here in LP spaces. So the same problem can be treated in LP spaces. Yes, thank you. So we can take, for instance, our space y in this case to be LP omega. Operator is the same. Condition about beta is the same. In this case, operator A, if P greater than 1, the operator A still remain M accretive for all P greater or equal 1. Here we should be careful, because for P equal 1, the space is reflexive. For P equal 1, the space is not reflexive. So for P greater than 1, we have strong solution. For P equal 1, if you start with initial data in the closure of the domain, we have weak solution or mild solution. But it's not so grave. But however, it's not a problem, because even in this case, because the smoothing effect extends also to L1. So even if you start with initial data in L1, closure in L1, we have a smoothing effect. The solution, mild solution, which no EAZ exists, is pushed in the domain, and we can apply. So applies as well in all situation here. LP greater than 1.
What is the vector? Is it mapping from LP to the world space and the monotonicity?
data is considered in this more general.
No. Here is an accretive, not monotone.
You don't consider that.
Here we have the condition. This operator is not monotone. I specify the operator is an accretive. Accretivity is a property from an operator from X to itself. Monotonicity is from X to its dual. Of course, in Hilbert space is the same thing. So it works very well, yeah.
But for in the case of L1, you change the domain, or you.
No, of course you change the domain. In this case, in L1, we should take the domain A equal, it is equal with y in W10, the W10, W10 omega for each delta y, it is in L1.
So you smooth and you enter immediately that.
Yes, if you start, yes, here, it immediately, the solution comes into a narrow domain which can apply the result from L2, for instance. Yeah, that's correct. Yeah. Next example I say is a reflection problem. A reflection problem for parabolic equation, or more general reflection problem. Reflection problem is the following. Suppose that we have this equation, d dt plus a0y plus, I don't know this operator say, ay equal, let's say, f in a Hilbert space, y0, where a0 is self-adjoint, positive defined, okay? And dik is a normal cone, and k to a closed convex subset of H. So we have a closed convex subset of H. dik is a normal cone, that means nky, it is zeta with the property, the scalar product y minus u e greater than 0 for all u in k. This is a normal cone, and this is a reflection problem. Because the normal cone, dik, it is 0 in the interior, if the interior exists, and on the boundary, on the frontier, on the boundary, dik, it is a normal. Now, this is a reflection problem. In fact, as I mentioned, we can apply this operator a0 plus dik is an accretive if we have 1 plus epsilon a0 minus 1, k leaves invariant k. So, reflection problem in Hilbert space is practically solved. This is one of the conditions. The other conditions as well can be applied here to have M accretivity. Now, because the problem always is the fine condition and there is a sum of two maximal or M accretive operator is still M accretive. One of the conditions is this one. I mentioned this one because it's important in stochastics. And yeah.
Yes, I have a curiosity in fact because I see a similar formalism and a similar problem, but not exactly, when people speak about stochastic viability. Sure.
This is a viability. This is a viability condition, in fact. Is a viability condition.
Viability is it the situation in which you don't need to have reflection?
Yeah, to remain as a, yes, but you could stay on the boundary. Yeah, could remain on the boundary. So it is close to reflection. Yeah, of course. But this problem is not important only as a reflection problem, but there are many variational inequalities, free boundary problem with a different type of constraint which are written to this form. A large category free boundary problems, so-called variational parabolic problems, no? Because this is a variational parabolic problem, is a linear problem with constraint of reflection type. No. Should remain. In the moment we want to remain in a closed subset and we want to have a solution, we should arrange, we should have an agreement between, so it's okay.
Again, I can repeat my question.
Yeah.
Is about, you again have H, I think, Hilbert space here, because you assume H.
Yes, it's Hilbert space, of course. It can be treated as another framework as well, from V to V prime, for instance, yeah.
But in both examples, could you have also, so here you can have from V to V prime, so you can have Gelfand triple variational. But what about the space of continuous function, bounded continuous function in, say, example 1? Can you cover?
This is a very bad space. In principle, yes, but a few examples can be treated. Because it's very difficult in this case, in fact, sometimes to determine the domain. In principle, yeah. You can,
In principle, yeah.
in principle, but if you cannot see exactly which is a domain, yeah, it is as far as you can avoid the space. Okay, yeah. Now, next example. The next example, of course, is, I mentioned already, is Porous media equation. Porous media equation, let's say it is xt ddt xt minus delta beta x. F, take multivariate, x0 equal x. Beta x on the boundary is 0, where beta is a maximal monotone graph. In this case, this problem can be treated as an n-accretive equation only in two spaces. The first space, it is h is y, it is what, h minus 1 omega. Second is L1. Only in these two spaces, this operator, ay equal minus delta beta y, with a domain, natural domain, is m-accretive. No other space, no L2, not LP, not H minus 1, and L1. H minus 1 has advantage, it is an energetical space, but from physical point of view, it is a mathematical construction only. L1, it is indeed, has physical significance in all the model, physical model, for this nonlinear, because this is nonlinear diffusion equation, but is a Banach space. So what happens in this case? If you want to work in H minus 1, we can apply theorem 2, 3, which give existence of a strong solution. Even theorem 4, because this one, this operator A, in this case, is also a subdifferential. If in this space, in the case when y, it is H minus 1. Otherwise, if we want to work in the space L1, we have, for this equation, a mild solution. That means a solution which is given as a limit of finite difference scheme. Solution is only continuous and generally is not differentiable. The result extends also on unbounded domain Rn, for instance. Now, so this is porous media equation, but it's not only porous media equation behind this. For instance, two-phase Stefan problem. Two-phase Stefan problem can also be written into the same form. In this case, beta is an enthalpy function. It is Lipschitzian in this case. Two-phase Stefan problem is so. In porous media equation, beta might be, in general, is a polynomial or a polynomial function, but might be also a very singular function. The result is very general because beta might be here every maximal monotone graph. But of course, we need some condition, in fact, to have maximal monotonicity of this, but we'll not discuss about this here. Yeah.
But in this case, we don't have a smoothing effect a priori.
In H minus 1 we have.
Yes, H minus 1, but in L1...
In L1 we still have, depends. In L1 there are some results obtained in 80s, in fact by Evans and also by Pazzi, which gives smoothing effect for some polynomial function beta with certain exponent, not for all exponent.
It's always the technique of the subgradient. You need to write...
Yes, it is as a technique, energetic technique, in fact. You should find, we are smoothing the operator beta and find good estimates for derivative and pass to limit. Yeah. There, okay, in my book there is this. Yeah. Okay. So this is porous media equation. I want to mention this because it, only a few more examples. Already the time is quite over. What happens? What happens in the case of wave equation? In fact, hyperbolic problems. If you have hyperbolic problems of this type, delta y plus beta yt, with boundary condition or boundary condition and initial data, of course, if you write the system, this equation is a system where beta is maximal monotone graph. If you write this as a system, we get a first order differential equations for which the theory applies. I don't want to go. More delicate is this problem, where here we have nonlinearity in y. If you have nonlinearity in y, we do not have accretivity for this operator, but there are some devices which permit in fact to reduce. And I'll speak about this. So practically you can use also in this case the theory. What happens with Navier-Stokes? Navier-Stokes is a dramatical case because even for this, because it's a not nonlinear term for Navier-Stokes, is not monotone. But however, how we proceed for Navier-Stokes? Because every good theory should be tried also on Navier-Stokes. So let's consider, let's write directly Navier-Stokes in abstract form. A plus by equal f. y0 equal y0. A is a linear self-adjoint operator given by delta. B is an inertial term, not measured. Okay. We work in the space H, free divergence vector Leray space. Good. This operator, nu A plus B, is not monotone in this space. Unfortunately, it's not monotone. But what we are doing? We proceed so. And according to me, perhaps is the best way to treat Navier-Stokes equation. To have an existence, a simple existence proof. We take a truncation of B. We define this operator. B m y equal Vy is a ball norm of y v less than m. V is a space, H01 intersect H power V, take dimension 2 or 3. It works also in 4. And it is B y, its truncation of this is y over norm of y. In fact, it is m squared if I yv greater than m. This operator, this truncation, it turns out, this is good operator, that this operator A plus Bm is a maximal monotone. M accretive, that is. Maximal M accretive.
Quasi. Quasi.
Quasi M accretive. Quasi M accretive.
Quasi dipende da
Quasi,
M.
quasi M accretive. Sì, yes, depends on, sure. Quasi M accretive. No. Quasi M accretive, no problem. Yeah, but no, we are not going to pass with M to limit. We are not going to pass M to the limit. So, this equation, dym, but this is not trivial. That A plus Bm, it is M maximal monotone. We should use some perturbation theorem. Quite sharp. In fact, Cato perturbation theorem. But this implies that this equation, dm plus nu A ym plus Bm ym equal f y0 for each m has a smooth solution. We can apply directly theorem 2. Smooth solutions, a space in Hilbert space. Smooth solution. Okay, so we have ym, which is very good. Is in W1 infinite, is Lipschitzian, 0 th, with aym is in L infinite, 0 th. How to recuperate our solution? I insist, I'm not going to pass to limit because we are fine. No. On this equation, we get a priori estimate. If we multiply this equation by ym and aym, I find the following estimate. In dimension 2, n equal 2, we find that there exists a constant such that this is for all n. In dimension 2, on the whole interval. In dimension 3, we get the same estimate, mt, c, but for a small interval, 0, for a local interval, which depends on initial data. Which is a conclusion. If you push m greater than c, this equation here, this becomes b. So we get a solution for our Navier-Stokes equation. So we use this approximating not in fact approximating, with a priori estimates, because a priori estimate for this one are exactly the same as a priori estimate for this. Multiply by A, multiply by AY, and get the same time. So this means that the solution to this one for m big enough is the solution to this. And this is the existence. There are some advantages, in fact, here with respect to Galerkin method applied to Navier-Stokes. In fact, because here we can use for this equation, which is of monotone type, the whole theory of nonlinear semigroup theory. If we want, we can also fractional step method and so on, we can perturb it and so on. So this is the idea, that for m big enough, the solution of this equation is solution of this one, which is unique, of course, in dimension 2.
The constant C does depend on...
No, does not depend of n. Does not depend of n. This is important, because if you multiply here by ym, bm, ym, ym is also 0. Like in for B. If you multiply by aym is the same thing. No, it's not independent of C. So we get estimate for ym independent of C. Very simple, it's the same type of estimate, and yes?
Yeah, what are A and B? So if we have the usual equations, so what are A and B in those terms?
Excuse me?
If we have the usual Navier-Stokes equation,
Yeah.
what are A and B?
Bm, B, which is B?
What, I mean, if,
No, Bm, B is the usual inertial term. It is projection y,
okay.
and
Alright.
Bm, it is exactly this one, truncation operator B. Yeah.
Okay.
Yeah. So we can apply practically, in fact, to this one with no problems. No. So we can say that the theory applies, but through this trick, in fact, which is very useful, in fact, very useful because you can use exactly for this equation. Practically, this equation is the same as this equation here. No, but we cannot get more than we know from this standard theory. But perhaps we can prove in an easier manner, in fact, and okay. Perhaps yes.
Three-dimensional case.
Three-dimensional case, we can this estimate, but on a local interval.
So you get local time.
So we have coincidence by the local time, on local interval. It is exactly the same, no? But the possibility to, okay. Now, this is exactly I want to say about time independent. Now I'm going to speak next time about time dependent. Time dependent is a dramatical situation because, in fact, it's time dependent equation which applies to which applies to stochastic equation. No? This one only gives methods and the possibility to compare or what it is expected to have from the theory. No. Okay, that's all. Thank you for.
So, time for questions and comments.
Yeah.
What about the asymptotics? Like say a graph.
This is a different problem. There are asymptotics for.
So what kind of results are available? For example.
For instance, I can say that you have a gradient type system. The solution is going to equilibrium solution in weak topology. One of the results. The Fermos also LaSalle Fermos theory applies as well in this case. In general, the dynamic of the.
Is there an attractor?
Okay. In general case, it's much more difficult. Yeah. In specific cases, in specific situations. Yeah. Yeah, we can. If you have a, like if on every dissipative system, because they are dissipative systems.
So there is a theorem that says there is an attractor for.
Yeah, an attractor exists, but the problem is how it looks like. It's all not the existence of an attractor is not a big problem, of course. Yeah.
I would like to see a reference for that theorem. Maybe
Yeah. Okay.
More questions? I think we have to wait for those till tomorrow. Okay, tomorrow. Next Tuesday. Well,
Yeah, it seems so.
second lecture, yes. And thank you very much.
Thank you.